At AMD's E3 event, the company made great strides to showcase products that overall look good on paper, especially on the CPU side. Even still, as with anything promoted on a stage at the world's most bombastic gaming event, there is a lot of flashy marketing that deserves scrutiny to keep perspective of reality. We'll be looking both qualitatively and quantitatively at the scenario AMD used for its stream testing, showing the differences between X264 fast, medium, slow, and more, while also showing tuning with process priority and FPS caps. This video will discuss why we think AMD's streaming presentation was needlessly misleading, especially since we agree that the CPU should handle streaming workloads more capably than the 9900K competitor. If you're already better at the game, there's no reason to stack the deck. Before that, this video is brought to you by us and the GN Store. The best way to support our independent reporting is through store.gamersnexus.net. Viewers like you allowed us to recently switch to paying for all of our own flights to product launch events rather than accepting flights from companies. This is made possible with your purchases of merch like our GN Medium mod mats in stock and shipping now and designed with GPU teardown diagrams and grids. Our 100% custom-made two-tone shirt is also a great way to help, and it's currently on sale. The shirt uses 95% cotton and 5% elastane for a sporty fit with vibrant colors and was designed entirely by the GN team. Learn more at the link in the description below or go to store.gamersnexus.net. Let's be very clear here. We're not saying that Ryzen 3000 won't be good. This is a matter of scrutinizing a specific part of a marketing presentation. That's what it is. And we've done this for just about everybody. So it's important to do this because our job in the industry is to be a reality check. And that's for the companies and for viewers, for people who are buying the product. And this did deserve a bit of a reality check. So what we are saying, one, not that Ryzen 3000 is bad or going to be bad. It actually looks promising on paper, although wait for our benchmarks. And then two, we're saying that some of AMD's presentations were misleading and do deserve some additional information shed on them. So today we're focusing on the AMD streaming demonstration. We already talked about AMD's attempt at measuring thermals with the Ryzen CPUs in our Navi and Ryzen announcement video, or the specs disclosure video, and that was a whole separate thing. But the streaming demonstration mostly amounted to laughing at Intel's 9900K, saying, haha, it does 1 FPS. And that is probably, for the most part, a reproducible number. It's not, we didn't 100% replicate it, but it's close enough that it doesn't matter. Because in a stream, if you're not playing at a reasonable FPS and you're below 10, it's irrelevant. It's all bad. So it is a number that can be replicated. The benchmark in that regard is sort of accurate. It's just that it's misleading. And that's the hard line that we draw and we need to explore today in this video. So one of the things AMD said here is that with the 12-core CPU, quote, you can do things that you couldn't do before. The other guy with 8 cores, sorry, which is sort of throwing the AMD 2700X under the bus as well, which is a very capable streaming performer, by the way. Although AMD sort of disclosed some of its testing procedure, it was still misleading for being an inaccurate representation of the need to use the settings that were shown in the demonstration in a real environment. So before anyone starts slamming the keyboard, typing in the comments section below, we'll remind you of this. Many enthusiasts felt that Intel's principal technologies benchmarks were misleading. So if those same people are arguing that AMD wasn't misleading strictly on the basis that it disclosed its testing approach, that's a double standard. We saw a lot of that on Twitter and just wanted to address it now. Principal Technologies disclosed in far greater detail how it tested, to the extent that we were able to really burn them with it. We literally showed up at PT's doorstep to ask about the benchmarks that it ran for Intel versus AMD at the 9000 series launch. So their results, like AMD's here in the streaming demonstration, are replicable, they're repeatable, you can reproduce it in your own lab. But that doesn't mean that they are realistic or representative of any real use case in the real world. It's more similar to hiding tessellation under the world and then demonstrating that one product runs this workload better than the other while neither receives a visual benefit. Our quality comparisons today will help illustrate why slow settings don't only add zero value for gaming content, but actually have no perceptible impact on quality when tested and compared properly. This is true for locally recorded content and streamed content, but especially streamed. And further, even the core-deficient 9900K relative to the 12-core CPU can be made to stream perfectly acceptably at still high-quality settings. The AMD presentation may have made it seem to some like the 9900K can't stream and game at the same time, but that's far from the truth. As a quick aside, our thanks to EposVox on YouTube for helping converse with us about stream quality concepts and for talking through some of our ideas. EposVox runs a channel based on improving stream quality and game capture visuals. We'll link him below. He provided some of the X264 flags that we played around with for stream tuning today. Let's start with an on-screen comparison showing the different encoding modes. It helps to visualize things, so we'll start with this and we'll explain more of what's going on later. We'll change the different encoding modes on the screen occasionally so that you can see the differences between them. As you're watching, try to discern the differences, if there are any, between the different encoding modes as we change them. Try to guess which mode is fast, which is slow, and which is medium, and keep in mind that the slower in name, the, in theory, higher quality, at least for the things they were designed for initially. So for example, slower or placebo or slow would be better quality in theory than medium or fast or very fast. But the reason in theory is in there is because it's not always the case, as you'll see today. So this was all captured on a 3175X. There are never any dropped frames, and we can strictly look at the image quality without the variable of performance. If you've been waiting for the encoding mode to change while I've been talking, we actually have been changing it. We'll label each of them now with slow, fast, and medium. Watch these sequences play back for a moment and try to keep tabs on if you see any differences in the image quality. A huge note here, some benchmark scenes change slightly, like the clothes that characters wear or the vehicles on the road, so it's important to pay attention only to static objects. In some games, like GTA 5, we're able to get much more consistency and avoid those issues altogether. A lot of games, like The Division 2 and Far Cry 5, which we'll show briefly as an example, have dynamic lighting in even the benchmark scene. This means that these particular games are useless for comparison because a lot of the argument online revolves around people thinking that they see a difference in the shadows. Well, if the clouds move and the lighting is affected, it'll look different because of the game, not the encoding choice. So we've eliminated these types of changes as best we can and just gone with games that stay more static, aside from elements like character clothing. Now that you've had some time to pick between the three settings for the best quality that you think you've seen, we'll reveal what each is. Actually, we bait and switched you. All three of these were not only the same encoding option, but were the same exact video. Nothing changed. We did this because we're trying to encourage people to be open and self-aware about having a bias. We all will, so it's best to just acknowledge it early and figure out what it is. There's no shame in a preference, just make sure it's over something that actually has differences. All three of these were exactly the same video overlaid and sort of fake switching between them. We'll drop the tricks now and actually show you the differences. We're going to use 1, 2, and 3 labeling for a moment so that we don't influence your opinions with the actual titles of which setting is used. These scenes are actually switching this time between 3 different captures with 3 different encoding presets, and we want you to try and perceive a difference. Again, the 1, 2, 3 labeling is a check against bias, and we'll reveal them in a moment. All 3 are used with a 10 megabit per second encoding option, just like AMD did. We've actually used this in the past too, and they're locally captured. But we also did separate streaming tests. Local capture was necessary for this comparison for one funny reason. With the streaming tests, although it worked for comparing them internally, it's a terrible idea for this video because then we would have to download and re-upload the stream, and then you just compound the compression. So it's a terrible idea for this video because you'd be looking at a result which has now been compressed and rendered several times instead of just the once that it needs to go up the first time, aside from OBS, obviously, in the initial capture. So by taking this route, we're actually giving AMD the benefit of the doubt, much like they claim to do for Intel, although that's a different story. And we're doing that by uploading the highest quality possible within the settings used. Remember, once uploaded, you hit upload or compression by the website. That further mitigates the differences between those quality choices. That's a big part of the story here. Let's overview the basics while you watch these comparisons a little bit more. Keep in mind that smoke or fog effects changes our in-game dynamism, and that they may have some procedural elements in the games as well that are not affected by encode quality. X264 is an encoding option available in OBS and other capture software and in rendering software, and is used in conjunction with the CPU to live encode video capture for stream viewers or for upload later. In OBS, you have the option of X264 CPU encoding or GPU encoding, whether that's on NVIDIA or AMD, like NV Encoder. The X264 library has dozens of options that can be tweaked, but most users will choose between ultra fast, super fast, very fast, faster, fast, medium, slow, and slower. That's all the presets, really, but you'd typically do that instead of hand tune your own options, which is possible. You could actually do that. The slower the encoding option selected, the more resources it requires. In theory, image quality increases, but there is also a placebo level of quality at some point, and there's also a right place to use each of the settings, like slow and slower, and it's not typically game streaming or capture, if ever really, but the bit rate at which games are streamed and captured is also lower than high quality media like you might get from a movie or something. Most streamers use Veryfast or faster if streaming on the host system, that'd be the system playing the game and streaming at the same time, with a bitrate likely of 6 megabits per second max. Twitch does not permit a stream greater than 6 megabits per second, but YouTube does, so we actually don't have too much of an issue with AMD's use of 10 megabits per second bitrate. We actually use that bitrate for our own testing because we use that bitrate for our own streams to YouTube, and so we aren't too concerned with that aspect. But if you care only about Twitch streaming, just keep in mind that you're more interested in 6, not in 10. And for our benchmarks, and you'll see them when the CPUs come out, we do actually benchmark both 6 and 10 so that you have a representation of each. Now, determine if you think there was a difference between 1, 2, and 3, and make a note of which you thought looked best. When we reveal them, if you thought fast or medium looked best, that means you are in potentially placebo territory, and there's probably no actual meaningful difference between the captures. You were just trying to find one, which is okay. We did that too when we first went through these tests and tried to discern the differences. So let's reveal what those clips were now. We'll explain some more while they play back with the proper name revealed. You'll see these frames repeated from earlier. And we might add a few additional quality settings in here for you. Very fast, we'll start showing up and showing some compression differences where the others don't necessarily, but we maintain that slow, medium, and fast all look functionally equivalent locally, and that should be doubly true once uploaded. There may be some small pixel-to-pixel differences, but they won't be quality differences like better or worse. It's just how YouTube at this point is processing it, and if it is a problem, we'll upload it somewhere else uncompressed. Although that is part of the point here too, is that YouTube does compress. But anyway, as for what each mode does, while that runs through some more, here's a breakdown. Slow versus fast, which is usable on the 9900K, by the way, and we'll prove that later, keeps adaptive quantization to mode 1 for both settings, enabling adaptive quantization, the ability to redistribute bits within a frame. Going up to mode 2 would redistribute bits across the entire video, which isn't useful here, and going to AQ mode 3 will net more distribution to dark parts of the scenes. But that option is not enabled in any of the presets, and we're on 1 for both of these two being compared. Slow changes B adapt to mode 2 from mode 1 with fast and very fast, which changes to a slower and newer algorithm that suffers a speed reduction with a higher B-frame setting, or bi-directional frame. But our chart shows that B-frames in both fast and slow are the same, and B-frames will provide a pixel delta that contains only the information from changed pixel values frame to frame, but not the absolute value for every pixel in the frame. These act as an intermediary step in the temporal process. For example, the change from frame 0 to frame 2. The newer algorithm will process slower, but does not improve the quality output in a gaming stream. It takes more resources to run without any added value. Remember, a lot of these settings are for video transcodes and encodes. And as EposVox says, again linked below, more for pixel junkies and enthusiasts than they are for game streaming, where the value is anywhere from low in the value add to non-existent. Here's a chart on the screen again to help illustrate these, sourced originally from archived site Beandog. D-block remains the same between slow and fast. This setting impacts encoding quality and time more heavily than some of the others, but only changes with the ultra-fast preset. Slow changes direct from spatial with fast to auto, which means that slow will choose between spatial and temporal, particularly in a multi-pass encode, where each option can be attempted and then the better choice can be kept. It sort of averages along the way, and that second pass you get some additional data. Much of the usefulness is lost in a single pass game capture environment, particularly one where we're working with relatively low quality to begin with. More notably, slow changes ME from hex to UMH from the ME GUI Wikibooks entry. This change is, quote, considerably slower than hex, but searches a complex multi-hexagon pattern in order to avoid harder to find motion vectors. Unlike hex and DIA, the ME range parameter directly controls UMH's search radius, allowing one to increase or decrease the size of the wide surge. This should theoretically help with motion, ending the quotes there, but as you'll see in our demos, there really isn't any tangible difference with a game stream. Slow also changes look ahead to 50, measured in units of frames, up from 30 with fast. This means that 50 frames will be used for rate control, and with regard to MB should theoretically increase video quality at the cost of speed. But again, a lot of this will depend on what kind of video you're encoding and for what purpose. H.264, after all, wasn't invented for this purpose solely. It wasn't made for game streaming. It does a lot of other stuff, and we use it to encode all of our videos too. There are a few other changes, and you'll see them in the chart, but what ultimately matters is the quality comparison in this use case. It comes down to a qualitative look. Performance is the other angle of this. Getting into performance, we'll be looking at streaming benchmarks using the Division 2, just like AMD, but we're going to run at 1080p locally and streamed. This is because the 1440p local setting that AMD used created a GPU constraint on the host system. They did stream at 1080 though, and this artificially limited the player side performance to bring the Intel CPU even with AMD's CPU. It also creates enough GPU load, with AMD running at nearly 100% GPU load during its stream, evidenced by the in-game UI on the right side of the screen. It's enough GPU load that OBS will miss some of the frame renders. We believe this removes headroom for OBS's scene compositing, and when checking with Epos Vox, it sounds like he believes the same. This introduces variables that AMD should have accounted for in fair testing, but instead created. We'd be curious to see what the render lag metric was for AMD's test runs, along with the percent delivered within 2% of 16.667 milliseconds, as these were some of the only metrics not published. Starting with viewer performance, this is the output that the viewer will see when watching the stream, except represented as percentages. This testing was done with real live streaming over a fiber network. We tried a lot of settings, especially now that we know how similar fast, medium, and slow, and often very slow, will look to each other, and we found that the 9900K stock CPU, without any overclocking at all, with turbo duration limits enabled, and running at Intel's 95-watt TDP, it's capable of game streaming with 10 megabits per second, fast settings, with the Division 2 at ultra settings. Again, that's with turbo boost duration limits enabled. So we're running this thing properly stock, more so than almost any motherboard will do for you out of the box, by disabling the non-stock motherboard power override options. With fast settings and no tuning, the 9900K delivered 100% of its frames to stream, meaning that the viewer did receive a 60 FPS stream, while the player maintained a 119 FPS average gaming frame rate, with lows bottoming out just at 50 FPS. This is reasonable when considering the local streaming going on in the background. Streaming on the host system always hits 0.1% lows hard, even with the high-end HEDT 18-core CPUs, and can be improved primarily, if not only, by using a secondary system. This is what seriously competitive streamers should be doing to avoid frame time drops if they are actually competitive in the games they're playing and they need that frame time consistency. The only downside of the fast stream is that its frame delivery pacing sits at 51% within plus or minus 2% of 16.667 millisecond delivery. We're still within a few percent of 16.667 milliseconds overall, enough that we hit the 60 FPS deliverable target, but the frame pacing is imperfect and could be improved. This is actually more a result of the frame lag caused by the higher GPU load than by the CPU load created, but we can make some changes on both sides of things to try and address this. This is also something that AMD likely would have countered in its E3 presentation, but did not talk about or discuss on stage. We demonstrated this by carefully reducing the GPU load with in-game options, but by keeping the CPU load exactly where it was previously, plus or minus about 1% error. With these changes, frame pacing improves to 93.3% within plus or minus 2% of 16.667 millisecond delivery, and further demonstrates that AMD's test was flawed. There was too much GPU load in this scenario, creating external variables and frame lag because OBS is also running behind on the GPU resources it needs. This is why we spend so much time explaining our streaming tests when we do them, and often dedicating 10 to 15 minutes just doing stream tests. There are a lot of variables, and it requires a lot of care to do properly. And when I say dedicating 10 to 15 minutes, I mean in one video, where the whole video length might be 25 minutes. Anyway, going back to the ultra settings, by using real-time process priority for OBS, we can see that we improved the frame pacing to the viewer from the original 51% to 71%, but the reduction in our other chart was to 0.1% lows for the player. This too can be tuned out by keeping process priority targeted at OBS and setting an 80 FPS in-game cap. We're now freeing up CPU resources from the game, which is spewing potentially unnecessary frames for the player, and reallocating them instead to the much more important OBS. We now have a 97% delivery within plus or minus 2% of 16 milliseconds. This results in a high quality stream for both the player and the viewer, and can be tuned further with other settings if desired. Medium encoding delivers 59% of the frames to the stream, so is where the 9900K starts to struggle with this title. Ultimately, we found that medium encoding does work just fine for the 9900K in some games, but it depends on how intensive the game is on the CPU. In this instance, the 9900K has trouble. Out of the box, without any changes, it can do fast. And with some small changes, it can start to do fast with a near perfect delivery in terms of frame pacing. But it's already pretty good. It's good enough that most viewers won't really complain. And if you're a professional streamer, you'd either want some heavy tuning on there, like some of the stuff we've done in here, plus additional X264 tuning, or you just get a separate system and really do it the proper way. Slow is too abusive on the 9900K for it to handle on its own. Some tuning with priority and FPS capping boosts it to 30% frames delivered, but that's obviously an entirely pointless stream with very low viewer quality. AMD will almost certainly win in this comparison, but it's a pointless and misleading victory. Ultimately, just like running a game with tessellation under the map, Crysis 2 will make AMD look worse than NVIDIA. The actual visual quality is not improved, even though the FPS looks different. Whenever we've used slow in demonstrations in the past, we've been extremely careful to outline why it's not a useful comparison beyond a purely synthetic workload. Our issue with AMD's presentation is that it wasn't presented this way, but instead misled viewers to believe the quality would be meaningfully superior. At the end of the day, the comparison should have been something else, because realistically, the 9900K can stream every bit as well as any of you will ever need for a single stream. Slower isn't actually better here. Anyone getting more serious should be using a secondary system anyway, because the frame times will always be more consistent without background processes, something we've extensively shown in the past. A better demonstration would have been AMD demoing its likely capability of managing 2 simultaneous live streams to both Twitch and YouTube for people who have multiple audiences, something that the 9900K would struggle with without using any rebroadcaster service. Another great example that we would have loved to see AMD use would be doing a local recording with X264 and also doing a live stream. This is useful if you're a streamer who wants to upload to Twitch Live and then maybe upload bits and pieces of your performance to YouTube later without having to re-download the VOD through Twitch, so you retain a lot of that quality. This is a valid comparison and one where the 12-core Ryzen CPU would probably win. We don't know for sure because we don't have it, but almost certainly it'd be better than the 9900K at it. Well, certainly it would be actually, and it probably would be good enough to do both of these things with very fast or maybe fast or faster settings, not slow, but something that's actually useful. A dual stream test has some real use cases and would still have had AMD in the lead, but in a more useful, realistic metric. We're not trying to say AMD won't be better at the slow comparison. It's just that the comparison is useless and misleading because it provides no value and a massive performance hit. If anything, we're trying to help AMD marketing better represent its own product. Finally, looking at the chart for player side FPS, we're hitting 147 FPS average with baseline performance. This metric highlights the CPU without any streaming constraints, functionally an unhindered gaming frame rate, and is useful for illustrating the impact to frame rate and time that streaming has. Going down to 10 megabit per second and fast, from baseline we maintain 80% of the original speed while also maintaining a 60 FPS live stream, albeit with mixed frame pacing results. Instituting a frame cap obviously caps the frame rate to 80 FPS, but does allow 0.1% lows to climb back to 50 FPS while improving frame pacing to near perfection on the stream side. You can also see that the slow settings, aside from the frame capped one, maintain a high frame rate. This begins to show a resource allocation issue compounded with an overall lack of sufficient resources on the Intel CPU for these unmodified presets and for the stock clock hardware. That frame time hit by adding a stream always brings us down to 50 FPS for 0.1% lows in the best case in this game, and when looking at the better performing options, you'll see that's true across both of them. In previous testing, we have illustrated that this happens on both Intel and AMD, sometimes with much worse 0.1% lows, and it's the nature of live encoding from the system that's also hosting the game. So that's it. That's really all this was. It was, okay, they're testing this with slow settings. Let's explore this. And a couple of things here. We are happy to take credit for being the ones to popularize this type of test. So we started doing this around the 7900X launch, and our first set of testing, or one of them, was to do dual streams, where you broadcast to two services at the same time without a rebroadcast service in between to eat quality or introduce latency. And that's a valid use case, sort of, but it's a rare one. Another use case we've tested in the past was local recording and streaming, and that's where we think AMD should have focused its attention, because it's a very valid use case for streamers who are serious about pulling some of their content, uploading it to YouTube in bits and pieces before someone else captures it off of Twitch and re-uploads it under a different name. So another valid use case. AMD's one of their former marketing team members told us in person that he had borrowed some of this testing methodology for their own marketing presentations, which is fine. But being that they did borrow this in part from us originally, whether or not the on-stage presentation did this at E3, we obviously we knew the deal. Like we've done these tests, we knew what we were looking for, and knew what was reasonable and what wasn't. So anyway, the biggest problem we have with the test is that it has already propagated a mentality that this quality preset in OBS is somehow advantageous in any meaningful way. That's the keyword, meaningful way. We can't see it if there is one. So there are places where these other quality settings with X264 or H264 if you prefer, are useful. And as Epos Fox said, pixel junkies, maybe if you're converting files or transcoding videos that are higher quality, dealing with greater level of detail than something like a game would, especially streamed at 6 or 10 megabits per second, that's where you might start seeing some advantages. But for these purposes, it is not a tangible advantage. And that's the problem, is a lot of the discussion around this from people who've never done any streaming before or don't really know anything about it, haven't done any testing of streaming before, have no idea how it's tested. Those are the people who are out in forums, on Reddit, wherever, and defending a presentation with really, there's no reason to. Like AMD and their CPU, they'll do just fine in game streaming. They'll almost certainly be ahead in a reasonable use case for this application as well. It's just the matter of how threads work with streaming content. So this is something that AMD would have won regardless. We would have liked to have seen it with a real use case, not something that is synthetic to the point that, again, it's putting tessellation under the map in Crysis 2 and then showing that NVIDIA does it better. That's the same kind of thing that's happening here. So anyway, a lot of people thought that slow would actually improve the stream quality and started parroting the presentation, so we wanted to put this video together. And beyond that, there's this sort of fascinating double standard with AMD where when Intel or NVIDIA get criticized by the media, and we've done a lot of that for misleading marketing practices, there's a sort of peanut gallery that cheers it on. And then when AMD gets criticized, there's a big jump to the defense of AMD. But AMD's not a person being picked on. They're not a kid in the playground. AMD's a big company too. And AMD needs to be challenged for its marketing as well, especially as it gets bigger, it gets more confident. That's going to become increasingly important. So you don't need to find any reason to defend AMD, is what we're saying. And at the end of the day, we do this to everybody, just as a reminder, because some people did do the usual chill comments about this. As a reminder, we published a video at Computex last year titled Intel's 28 Cores of Bullshit. And then we also went to PT, Principal Technologies, visited them. We had a scene where we kind of counted from 3 down and flipped off the camera because of the testing methodology. With NVIDIA, we put them in our disappointment build and on a shirt that we sold a lot of for the disappointment build. So this happens to everybody from us. It's not meant to be personal. For those of you who are big AMD fans, please take a step back, look at the quality comparisons we did, and try to remove that bias and just think about, well, okay, so this wasn't really a valid comparison, but there are a lot of valid comparisons, and let's just focus on those. Because again, if you're already good at the game, there's no reason to stack the deck. And this is a matter of AMD has a lot of things that its processors are genuinely really good at. So we'd like to see those focused on, not creating these synthetic scenarios that will actually benefit nobody in the game streaming space, which is where it was targeted. So that's it for this one. Thank you for watching. Subscribe for more. If you want to support this type of content, you can go to store.gamersnexus.net to pick up one of our mod mats, larger on back order. You'll be guaranteed one if you back order it. And then medium are in stock. Or you can go to patreon.com/gamersnexus. Thanks for watching. We'll see you all next time.